Rockets are our vehicles of exploration of outer space. They are the carrying vehicles that carry satellites, rovers, and many other things out of Earth's atmosphere. Interesting, right? Yes, indeed it is. But there are many things that constitute a rocket: complex mechanisms, various stages, different types of engines, and many other things. Today we have with us Mr. Divyanshu Podar to give us insights on rockets. He is an alumni of Indian Institute of Space Science and Technology, Kerala, and has worked with ISRO in the past. He is very fond of rockets, and to expand the reach of rocketry in India and creating an ecosystem of model rocketry, he found Rocketeers, India's first solid fuel powered model rocket kit manufacturer. Rocketeers manufacture model kits for school and college students to increase students' interest in rockets. So, without further ado, I would like to call upon Mr. Divyanshu Podar to start with his fascinating talk. Thank you.
Can everybody hear me?
Yes, sir. Yes, sir.
Great. I will just start with this. I'm really sorry for this being slow. My system is hanging for some reason. Just bear with me for 2 minutes till this gets smooth again. Yeah, can you? So okay, we'll skip the first slide. So everybody can hear me, and can you guys see the first slide? Hello.
Sir, actually, the PPT is not visible right now.
It's Is it there now?
Yes, sir. Yes, sir.
Great. So, hello everyone. Good morning. And we'll today talk a little bit about rockets, how rocket science evolved, and like what kind of rockets we are building now. I'm going to tell you a little bit more about model rocketry and the kind of opportunities that exists in the world of rocketry and rocket science at large, and what are the career opportunities both in India and abroad. And that's how we'll wrap it up. In the end, we'll take some questions from the audience members. So let's begin. So first, over here, as you see, I want to talk about rocket science as it evolved, the history of rockets. So rockets sort of came into being for the first time. So there's a little bit of a discrepancy between where exactly, but there are two major historical events where we see rockets becoming a reality for the first time. First is a Chinese internal war with the Hans, and the second is Tipu Sultan. So both of these people they invented rockets to fire them onto the oncoming army, and these rockets were small, sort of crude, and did not have a lot of range or firepower. But they were they were weapons that were ahead of the time at that point of time. It's almost 400-500 years ago, and things slowly evolved. We saw rockets become fairly prevalent in the form of missiles during World War II. These were dropped down by planes. There was a lot of German blitz. It was called the German Blitzkrieg. So what the Germans used to do was they used to have hundreds of planes loaded with thousands of rockets, and they used to fly them over one country. Let's say they're flying over Italy, with all of these thousands of bombs being dropped onto these this whole country. So it was a blitzkrieg. They used to blow up the complete city in a single blitzkrieg. So that was the most sort of second prevalent form of rockets that we saw. After the Second World War, rockets really started becoming more commonplace, where we started seeing things like ICBMs, which were still very weapon oriented missiles and stuff. But then around the 50s and the 60s, we started seeing civilian use, where we started looking at these rockets as a sort of a vehicle, or as a sort of a system that could help us create a lot of value for the people of Earth, that would help us understand the Earth better, that could help us understand physics better, that could help us monitor our weather better, that could help us communicate better over longer, larger distances. And that's where we started seeing launch vehicles start to come in. In the initial days of Gemini program for the US, and the initial USSR space program, we used to see these small rockets. We saw Proton ka first version, and stuff like that. So we saw Juno, which you see over here. These were small rockets. These were capable of carrying up to 1.5 to 2 tons to low Earth orbit. And during that time, satellites started getting built. At that time, we did not even have a lot of satellite technology that could really be deployed. The first satellite, I'm sure you all know the name of it, was called Sputnik. So Sputnik, and this name is really in our consciousness right now, because we also have a vaccine for corona. It is just called Sputnik 5. So the Sputnik satellite by the Russians. So those that satellite, it was approximately the size of a beach ball, beach volleyball, a little bigger than a basketball, and it had two antennas coming out of it. And this satellite, the only function that it performed was that it used to beam a signal from the satellite. It was like tung, tung, tung. This was the signal. So it was a constant beeping signal that was there, that it was beaming down on Earth. And anybody who had a radio receiver or a satellite radio receiver could capture the signal when Sputnik was passing over that region, and see that yes, there is actually now an object that humans have placed into space that is going around the Earth, that we can capture a signal from. That was the only function of Sputnik. It did not really perform any other function, but it acted as proof of concept that yes, we can do this, and this was made possible because of such rockets. Now, as we started realizing that we can do this, we started making these rockets bigger. We wanted more functionality. We wanted to be able to do more things. So, as you can see, the rockets start getting a little bigger over here. In the center of this slide, you can also see the PSLV. It has the Indian flag below it. So, the PSLV sort of started flying in the 90s, and today is sort of the workhorse of the Indian space program. It's a very, very reliable vehicle. I'm sure all of you know the name SpaceX and know the name Falcon 9 and so on and so forth. PSLV, even after all of that, even after all of the reusability and all of the modern sort of technologies that go into building something like the PSLV, even after all of that, into the Falcon 9, even after all of that, PSLV till today still tends to be the cheapest rocket in the world per kg of launch mass. And this is one of the greatest achievements of the Indian space program, and it does really interesting things. It actually up till very recently held the record for maximum number of satellite launches in a single launch, and I can sort of show you a little bit of that. So we'll see the PSLV and how it launches and how it deploys these satellites. So can you hear the audio?
Yes, sir.
You can hear the audio, right? Great.
So actually audio is not clear. So if you hover your mouse on the top of the screen, you'll have option to share computer audio.
I am sharing that only, I guess. Anyway, did everyone could see the video, right?
Yes, sir. Yes, sir.
Yeah, so what I'll do is that I'll explain. First you saw the launch, and in after that you saw the booster separation. The boosters are all smaller rockets on the side of the main rocket. So this was the PSLV. It has 6 boosters. First they separate. Then you have the nose cone, a heat shield, which is called, or payload fairing. So that separates because you're already above 100 kilometers, 110 kilometers. So the atmosphere is not there. So you don't need the heat shield or the payload fairing anymore, and hence you sort of see that separating first, because the lower the mass that the propulsion system has to push forward, the better. After that, you see the separation of the third stage, then you see the separation of the second stage, and then you see first stage, second stage, and third stage, and then you see the satellite deployment happening. So the satellite, in the satellite deployment, first you see the deployment of Cartosat and 2 ISRO nano satellites. After that, you see that the rocket is turning. So if you notice carefully over here, I'll just go back to that part again. See if I can. So see, this is on your screen, the Cartosat satellite right now. Can everybody see that? Hello.
Yes, sir.
Yeah. So this is the Cartosat satellite. This is basically an Earth observation satellite. It helps us oversee our oceans below the Indian landmass. So this gets deployed, and you will see 2 other nano satellites. And right after they get deployed, you will notice that the rocket, or the place where the camera is mounted, that component starts turning away from these. It's not just that they are going far away, but you see, like it's like taking a right turn, and you should try and notice that. So if you if you noticed, I'm really sorry, my system is really hanging today. I don't know what's wrong with it, and because of that it's becoming really clunky. But so if you noticed, the Cartosat and the screen on the top left corner, and the rocket has turned. So what the rocket is right now doing is that after releasing the Cartosat and the 2 nano satellites into a singular orbit, it then changes its direction, changes its path, goes to another orbit, a different orbit, and releases the remaining satellites, which are the doves, the nano satellites that you were seeing, that keep coming out of the rocket, one after the other, after the other, after the other. So many of them, almost as we saw. like the total number of satellites was 104. So out of that, almost 98 were these Planet doves. Planet is a satellite manufacturing company and based out of the US. So it was their satellites. So this is called an orbital change maneuver. This is one of the few rockets. PSLV is one of the very few rockets that's capable of performing this function, because it has fourth stage as a platform functionality, where the fourth stage can ignite, reignite, change orbits, go into different orbits, and release satellites wherever required. We have already done orbital injection for 3 different orbits in a singular launch. So this is the kind of sort of capability that India has developed with this rocket, and it's done in a manner where not only is it one of the most cost-efficient methods in the world, but at the same time, the philosophy of the Indian space program has always been larger public impact. So, as I told you, rockets evolved from the perspective of weapons, and because of that, any space program across the world, whether it is NASA, whether it is Russia, whether it is China, whether it is any of the European countries, all of these programs developed as a defense first program. It was a strategic and a defense and a national security perspective, because of which US said that, okay, we need to build rockets, we need to build satellites, we need to put a man on the moon, because there is national pride associated with it, there is national security implications because of that. But India, when they started ISRO, when Dr. Vikram Sarabhai started the vision that we placed into our minds is to create a national space program for the benefit of society. And that philosophy, it was the world's, with that philosophy, it was the world's only civilian first space program. And that is why we see the Indian space program perform and behave in completely different ways compared to the global space programs, because we are not a defense first or a defense component space program. We are a program that is looking at a very core, at the very core level, how can space be used to benefit society over here on Earth, and we develop everything that we want to based on that. So as these rockets were evolving, Indian space program was also evolving. And over here you see the first rocket in this image is the GSLV. Is a GSLV Mk2. Actually, we now have an Mk3, which is a little bigger. Like, it is shorter in height, but it's a little more powerful than this. It kind of looks like the Ariane 5, which is the fourth rocket in this picture. And we see that the rockets started getting bigger, and things started getting a lot more interesting, and you could do a lot more payload, you could build a lot more interesting things. Because of using stuff like this, we were able to build. So if you look at specifically over here, the space shuttle, it was instrumental in building the space station, the International Space Station. And it is because of rockets like this that we could build the International Space Station. If you look at on the rightmost side, the Chinese rocket called Long March 3B, this is the previous version of the rocket, Long March 5, which is used by the Chinese space agency to build their space station, which is now getting built. You must have heard the news very recently. China launches a rocket and it is going to land uncontrolled somewhere in the earth. It landed in the ocean near Maldives. So that rocket launch was actually one of the first rocket launches for the Chinese space station, where they are looking to build the space station, where they are assembling something right there in space. So these are the rockets. These are the kind of rockets that come in handy for doing activities like this. So if you've noticed throughout this all, that there is a rocket and then there is a satellite. Satellites are the satellite or space station or something or the other that is going inside the rocket to space, like Sputnik or whatever. And then that thing is actually the thing that we are using. We use Cartosat. We use all of those nano satellites. We use the space station, but the rocket, it gets discarded, and the rocket is not really going to get used again. So there are two ways to look at the rocket over here. First thing is, you can think about trucks. So when you have a computer lab in a school or your college, for example, all the computers will come to you in a truck. Then you will use those computers for the next 5 years, 7 years in that lab. but you don't think about that truck again. So these rockets are like a truck. They are like space trucks. They are actually bringing the computers that we need to space so that we can do whatever we need to do. But the purpose of the rocket itself is just transportation. It is just a launch vehicle. It is just the purpose of for the purposes of taking X equipment from place A to place B. So that is the only purpose that any rocket might fulfill at any point of time. Second thing is that we are not reusing them again. Now imagine if your computers came to your institution and then you had that truck and you threw that truck away instead of letting it go back. So your cost of transportation would be more than the cost of computers. And that is exactly what happens today. When we launch these satellites, the satellite itself is less expensive, but the cost of taking that satellite up from Earth to space is more expensive than just the even the combined cost of all of the satellites that were there in that rocket. So this creates a very different sort of a problem set, and because of that, access to space has always been very limited for all mankind. And then Elon Musk, I'm sure all of you have heard the name, started this company way back in 2003. It is called SpaceX, and they started building these rockets where their perspective was that rockets should be like trucks, planes, cars, boats that cannot be used just once, but can be used again and again and again and multiple times, and they should be reusable, and we should be able to, really see how we can sort of get benefit out of these rockets. And so with that, they started developing something called reusable rockets, which have a propulsive landing. So space shuttle over here tends to be reusable. People think that acha, space shuttle is like the space plane, right? But space shuttle was never really like the space plane, because when it landed back, it required so much refurbishment that the cost of refurbishing the space shuttle and the time taken to refurbish the space shuttle was in itself very high. And it was not like reuse. It was like every time your truck goes out, it delivers its equipment, gets into a serious road accident, and then you get it back. So now you have to repair the full truck before it can make one more delivery. Now next time it will make a delivery, again it will get into an accident. This accident is called re-entry. So during the time of re-entry, every time the shuttle used to get severe damage and severe refurbishment and repairs were required for it to be able to fly again. And out of this also, you see that the space shuttle has one space plane like thing in the front, and behind that it has three rocket boosters, two white colored ones and one in the center. So the one in the center, the orange one, that was not reusable. It was single use only, so it had to be built every time. And the two white ones used to fall back into the ocean, and again we used to take them out of the ocean and refurbish them. Again, the amount of refurbishment required was very high. So this was a problem that this is a problem, was it still is a problem, even though we see some proof of concepts now which tell us that okay, we can make rockets reusable. And I'm going to show you some of that now. So I hope the audio was better this time, because I love the audio on this file. So yeah, you guys saw that video. That was the Falcon Heavy rocket. Over here you see Falcon 9, which is the previous version of that. And Falcon Heavy today is the most powerful rocket in the world. And that was the first flight you saw. So whenever we launch a rocket for the first time, usually what happens is that we put a concrete block inside it, a big concrete block, to simulate the weight of the payload. But SpaceX decided that instead of putting a boring concrete block, they will send a car to space. This is a very interesting sort of a mission. It really captured an imagination and inspiration for a lot of people. So interesting to see a car going, and it's like a car driving in space. On the radio, there are two songs playing. One is Rocket Man, and another one is a David Bowie song. I forget the name. Both of them are very spacey. The PCB of the car says "Made on Earth by Humans," which is a very interesting way to put it. And it has all kinds of interesting data. It has an ARC disk, which has when the time it was launched, it had a complete copy of all of Facebook, all of Wikipedia, all of a lot of Google, and a lot of other sort of human history stuff. It had the complete Britannica encyclopedia. It had a compendium of languages. So all of that data it's carrying with it. So if an alien civilization finds it, they would probably be able to learn a lot about humanity. So that's and in the end you also saw that two of these rockets came and landed back, and now you can put a new payload on them and launch them again. And so SpaceX has been reusing these rockets again and again, and they have already shown that they can reuse the same rocket almost 10 times, 11 times. So actually, as of 4th May, they have used one of these boosters 10 times. So that's a really long way that they have come to showcase that yes, rockets can be reusable, and we can do super interesting things with them. Over here, the third rocket from the right is what you see as the Falcon 9. So this is how these rockets are evolving. And on the rightmost two rockets that you see, the first one is called N1 rocket, which was the Russian moon rocket. They tried to build it 4 times. They tried to launch it. All the 4 times it blew up, and that's when the Russian space program shut down. And the rightmost rocket that you see is called the Saturn V. This is the rocket that Neil Armstrong went to the moon in. And there were total 14 launches, out of which 2 were unsuccessful, 11 were successful. And that's what took humanity to the moon during the 60s. So this was just from my side a brief history about a very quick sort of a perspective on how rockets are evolving. They started off as weapons. We started learning that they can be used for civilian purposes to launch satellites and build space stations in space around the Earth. We also used some of them to take humans to the moon. But we realized that they're really, really expensive, and they get used only once, and it's a waste. And so we've now started building them to be reusable. We are learning how to make them reusable so that we can start thinking of going to the moon and to Mars, and to the outer and inner solar system, and really start exploring space and becoming a spacefaring species. In this process of trying to figure out how to make these rockets more and more reusable, and how to really draw the benefit that we want to draw out of them, we have so SpaceX has been advancing this further, and I will show you that as well. So this is the Starship vehicle that is being built by SpaceX. They're about to do a test flight, and this is supposed to be the vehicle that will not only be reusable, but it will be human rated. So it can take humans to space, it can bring us back, it can go all the way to Mars, it can go to the moon, and it can do all kinds of interesting stuff. And because it is reusable, it will be capable of, let's say, what will be the price of taking a human to Mars today? It would be approximately on the lower end. अगर to say it in a very crude way, सस्ता सुंदर लेके जाना है तो 300 मिलियन में जाएंगे. 300 million dollars, 300 billion dollars. Something like the Starship, if it becomes successful, this will do this in $300,000. That is a reduction of 1,000 times. So because it is reusable, and here we go. So what you see over here is this rocket falling back to Earth, and it's literally falling back to Earth. It's very very fast. It's falling uh, like a skydiver. So a skydiver has two arms and 2 feet out, and if they change the direction of their arms or the direction of their feet, they can control in which direction they will fall and how they will move. That is exactly how this starship is now falling back, and the four flaps are helping it. Yeah. And there you have it. So this was a Starship landing, and this is one of the first times that SpaceX was successfully able to land a Starship. And this is actually bigger than the Saturn V rocket that you see over here. And there's tons of content available on YouTube and otherwise on the internet. So you can check out more of it. It's something really interesting happening with rockets right now, and it's supposed to be really really game changing. It completely changes the perspective of how we look at access to space and how we look at sort of what will happen with rockets and what will we be able to do. It really shows us a path forward, and then in a way that's changing the space industry completely. It's reducing the cost of access to space by a factor of 1,000, and it's providing us with the opportunity to create technologies and create companies that were up till now a matter of science fiction. So it's for the first time that space science fiction is sort of we have the opportunity, and especially you guys as young students right now have the opportunity to build into reality during your lifetimes because of something like this. So this is a broad perspective on what rockets were and how they are and what they can be. So now let's start looking at what kind of fields need to come together for rocketry. So first thing that is there is the engines, which is the propulsion. The second thing that is there is cutting through the air and having an aerodynamic shape so that you have less drag. So that's the aerodynamics of it. The third thing that comes in is, which is really, really challenging and one of the most difficult fields, which is really underrated in terms of people's understanding. It's called manufacturing. So just designing the rocket is one thing, but manufacturing it is another. And manufacturing rockets in the right way has so that you can maintain quality and you can ensure that all kinds of tolerances are absolutely correct. And this plays a really really vast role. Just to give you an example, against a temperature difference from minus 90 degrees Celsius to plus 130 degrees Celsius, you need to have a tolerance of approximately 2 microns for the system to operate properly. So your material selection and your manufacturing technique has to be accordingly. And you have to account for heat expansion in such a way that your change in dimensions has to be less than 2 microns across that vast temperature range. So this is what manufacturing engineers and rockets do. Apart from this, you have this field called navigation, guidance, and control. These are the computer segments that decide how fast your rocket is going and what is the spin and what is the angle. Using all of this data, they tell you whether it's on the right trajectory or not. They communicate with the ground stations and overall keep the rocket in control. They help us with the navigation of it, take it to the right place. Then apart from that, we have payload integration, so which is a satellite, and the satellite being built by the satellite engineers has to be integrated onto the rocket, kept properly, and so on. So these are a vast array of fields. Even computer science engineers help us program the NGC system. So electronics engineers build a lot of the NGC system. So these are a vast range of fields, engineers from all different fields coming together. Even civil engineers contribute because they need to build out the ground station, the launch pad, and so on. So they need to understand how the system will work so that they can build a ground station or a launch pad which will work accordingly. So if you look at the current facilities of new space companies, actually some of them are hiring more civil engineers than aerospace engineers because they need to build out their facilities according to what they will need. And these are very, very specialized systems. So you need to build something very, very specific, very different. This is not run of the mill stuff. So a lot of these different fields come together to build and fly rockets, and all kinds of people have different works from their different domains. And when all of these come together, it's only then that we are able to really see this system perform as a whole. So now, just to give you from the very basic level, there are what are the types of rockets that you can sort of just see the principles with yourself. So this is a very, very simple pressure-based rocket where you can build a shape of a rocket, you can pressurize it with air using a cycle pump, and you can see what the trajectory will be like, and this all sort of behaves like a rocket. It's behaving on the same principle where it is pushing out mass, and that momentum gets transferred to the main body of the rocket due to Newton's third law of motion, and so the rocket gets pushed forward. Something a little more powerful would be a water rocket. I'm sure you guys have seen a water rocket competition in one of your tech fests. We used to have it in our tech fest, and it's a really fun competition. You can build a rocket out of a Pepsi 2 liter Pepsi bottle that can go up to 220, 230 meters, which is it's just a beautiful flight. It really looks like a rocket, and you can see that it's pushing out rocket like a plume. They're pushing out the water like a plume, and it's a really fun experiment. Very easy to do. And plus, like if you're building it out with a Pepsi bottle, you get to have the Pepsi too. So it's a very good deal. And then when you start getting a little more advanced than something like a water rocket, the next thing that comes up is a model rocket. And this is what Rocketeers does. And the purpose of model rocketry has been to teach students like you how do rockets really work. And this is not something which is just on a principle level, but this goes to a much deeper level. And just to give you perspective on this, the US ecosystem, where we see maximum amount of rocketry happening, is the country that has the maximum amount of space companies happening as well. They launch almost 12 million model rockets every year. Uh, if you walk into SpaceX, Planet, Boeing, Lockheed Martin, any of these companies today, and you take their employees and ask them how many of you have built model rockets and flown model rockets, you will see hands go up almost by 80-85%. These are people who have really captured model rockets is something that really captures their imagination at a very young age, provides them a tool where they can tweak each and every aspect, from the aerodynamics to the propulsion to the navigation, guidance and control to all kinds of other stuff, and see how this model rocketry can really translate to something which is much bigger. And Rocketeers has been working to bring this to Indian students because we believe that India up till now has been a country that has taken a completely different approach to rockets, and really worked for the public benefit at large. And we are one of the leading space powers of the world. So we need to create a large human resource pool that will build the SpaceX of India, that will build the space ecosystem of the 21st century for India. And for that to happen, we need to have a vast rocketry ecosystem. We need to have a lot of people coming in, really wanting to do this, really learning how to do this, and how they can contribute. And so for that, we have been working with model rockets. And just to show you a little bit of what model rockets are, I'm going to show you this fun model rocket battle by Dude Perfect. I'm sure all of you know Dude Perfect. And So I'm sure you guys enjoyed that. And so this is what model rocketry is like. It's a really, really fun activity, helps you learn a lot, and you can get all kinds of interesting outcomes where you have absolutely beautiful, amazing launches because you've built your rocket perfectly, or you can have failures of different types and sort of learn how to really tackle that. And we do that with rockets in India, rocketry in India also. So just to sort of show you that as well a little bit. So this is us working with IIT students in Thiruvananthapuram. And that's the parachute. So this is what model rocketry is, if anyone of you was wondering. And so this is like the step that really helps you understand rocketry to the core, and you can have all kinds of interesting experiments on this. You can add payloads to it, you can add satellites to it, you can add staging to it, and you can do all kinds of stuff that you can do with real rockets, with these rockets as well. You can actually make them reusable, just like the Falcon 9 or the Falcon Heavy. And if you want to check that out, you guys should check out this YouTube channel called BPS Space, and those guys show that. So this is a little bit about how what's the trajectory of flights like these, where there's a power descent. The power descent is the part where the engine is working, and then there's a coasting flight where the engine is stopped, but the rocket is still going up because it has some momentum of its own right now. Then it reaches the top place, which is called the apogee. Then it has an ejection charge which deploys the parachute, and then it descends with the parachute slowly. So this is what flight of the model rocket looks like. And just to give you a basic perspective, this is what are the major differences between an actual launch vehicle and a model rocket. So one thing that remains the same, if you've noticed, is that there are four forces through atmospheric flight. These four forces remain the same, and they're the same on all flying objects. They are the four forces that will control the aerodynamics of any flying object at any given time. And as you move out of the atmosphere, two of these forces go away, because out of these four forces, two forces are because of the air. And these two forces are lift and drag, and the remaining two forces are weight and thrust. So the thrust comes from your engines, the weight or the gravitational force is an inherent force, natural force that happens because of the Earth or any other celestial object. And then you have drag and lift, which are both aerodynamic forces, which are because of the air. So as you move out of the atmospheric flight, you don't have drag and lift anymore, and all you have to deal with is gravity and thrust. So it really is a different sort of an configuration when it comes to space flight. And the way objects behave in space flight is very different from the way objects behave in atmospheric flight. So we'll look at it from the perspective of, so imagine flying a plane, a paper plane. So when you fly a paper plane, you push it hard with your hand, and you see it go into the air, do some acrobatics, and then land on the ground in front of you. So what really happens? So when you're pushing the plane away from you with your hand, you give it a muscle force, which is like your thrust, which is like the engine of the plane. The air around the plane gives it resistance, which is like drag. The plane goes up in the air, that is like lift, and gravity is obviously, the weight of the plane is obviously acting on it. So these are the three forces that have come into being because of your actions, and gravity obviously was naturally acting on the plane. So these were the four forces, as we discussed a little earlier, and any flying object has to manage out these four forces to fly properly. So just if you've noticed, I've said that there are all these objects need to have an aerodynamic shape. What does that really mean? It means that you're designing the object such that you have minimum drag. Drag is the object that will stop you in the air, that will try to keep you in place. So if you look at a square plate, it has the maximum amount of drag. If you look at a ball, it has a little less drag than a square plate. But then when you start comparing it with an airfoil, which is like the wing of a plane, not only does an airfoil have very, very low drag, but it has high lift as well. So the reason that it has high lift is that the amount of distance that the air has to travel on the top of the airfoil is a little less than the amount of distance that the air has to travel on the bottom side of the airfoil. Because of this, the air at the bottom side of the airfoil moves a little faster. Moving a little faster means that it has more kinetic energy. So where does this kinetic energy comes from? This comes from pressure energy. So pressure reduces, and a reduction, so the I actually flipped it around. The air on the top is moving a little faster. So because of that, pressure has reduced. So you have higher pressure at the bottom and lower pressure at the top. And this pressure differential is what creates lift. So this is very, very important in planes. But when you are talking about rockets, we try to create a symmetric shape that does not even have the component of lift, because we want to take the rocket up using thrust. Lift is not the force that is going to help us take the rocket up into space. So thrust, if you've looked at it, if you've done an experiment with balloons, so if you can blow up a balloon and leave it, it will go around the room as the air gets pushed out, and the balloon will keep moving. If you attach a straw like this, you can make the balloon move straight in a fixed trajectory. So this is what acts like thrust. So in a paper plane, when we are flying, the thrust is only happening at the initial stage of flight. But in an actual flight, the engine is giving sustained thrust. So you can continuously keep getting lift, keep going further and further. And that's how planes actually go further than a paper plane. Like a paper plane has thrust initially, then there is no thrust. So as the speed reduces because of drag, the lift also reduces. Lift and drag are both, as I told you, because of air, and they are forces which are dependent on your speed, on your velocity. So as your velocity reduces, your lift will reduce, your drag will reduce. And as the lift reduces, your gravity, your weight will overpower the lift and your plane will land. But if you have constant thrust, you can always keep your velocity high enough such that your lift is higher than your weight. And so your plane can stay in the air and travel much longer distances. So this is just a quick overview of what we have learned up till now. We've seen initially what are the fields that go into rocketry, how four forces control the flight of a paper plane and every other flying object, how these things play out in terms of thrust and aerodynamics a little bit, and how Newton's law is sort of the law, third Newton's law is responsible for taking your rocket forward, because as the air gets pushed out or as some mass gets pushed out from the bottom of the rocket, that momentum transfers to the main body of the rocket and then pushes it forward. This is basically Newton's third law, that every motion or every action has an equal and opposite reaction. So so I'm not going to go into a lot of detail on this because I know you are all engineering students, you know this stuff. So now let's look at a little bit more in detail about solid rockets and what are the real sort of implications of rocket engines when it comes to launch vehicles. So there are three major kinds: solid engines, liquid engines, and cryogenic engines. Just to So just to show you the plumes of the three different types, on the leftmost side, you see a solid rocket booster. So this is a solid engine where the fuel and the oxidizer are combined into a single solid. So if you know, or I'm sure all of you know, that for something to burn, there needs to be oxygen in the atmosphere that it takes and combines with. So a burning reaction is basically consuming oxygen. So in case of a rocket fuel, what we do is that the rocket fuel and the oxidizer are both combined into a single chamber. In case of a solid fuel, they're combined into a single material so that the oxygen is available within the material itself. As it burns, this is passed through a nozzle to accelerate the flow. So the flow comes out at very, very high speed, at very, very high temperatures, transfers all of these energy in the form of kinetic energy to the rocket. And this whole material is encased into a singular casing inside a single casing just above the nozzle. This casing also acts as the combustion chamber. So in case of a solid rocket booster, the propellant tank and the combustion chamber is the same thing. The propellant is burning inside the tank that it is stored in. One of the advantages of such type of a booster is that you can get very, very, very high thrust, because the amount of propellant that you can burn in one go is very high, because you can have a large surface area in a large propellant tank burning at the same time. But the disadvantage at the same time is that the efficiency per unit mass burning, it tends to get low. Also, once you have ignited a solid rocket booster, you cannot switch it off and you cannot switch it on again. It will only switch off when all the fuel has burnt, completely burning out, and only then it will switch off. Then we come to liquid engines. In a liquid engine, you will have two different storage tanks, one for propellant, one for oxidizer. You will pass these oxidizer and propellant through a series of pumps and put them into a combustion chamber. Inside the combustion chamber, you will have a spark. Because there is both oxidizer and fuel present, they will start burning. As they start burning, they rapidly produce a large volume of gases at a very high temperature. This is then again passed through a nozzle. This nozzle accelerates the flow, and this whole energy is then transferred in the form of kinetic energy to the rocket. So now some of the disadvantages of a system like this is that you cannot get very, very high thrust like a solid rocket booster from the same liquid engine. But because you can only have so big a combustion chamber, but if the fuel and oxidizer is coming through some pump or some system, there will be only so much volume that you can insert into the combustion chamber at the same time. But in case of a solid rocket booster, the full propellant tank you can use as a combustion chamber. So because of that, very high thrust is not possible. But you can get much more efficient burning. So your mileage can be much higher. Your specific impulse, basically in rockets, the term for mileage is called specific impulse. So that can be much higher. You can have a more efficient burn. You can get much more kinetic energy from the system per kg of propellant and oxidizer. You can switch it off because you can stop giving oxidizer and fuel to the combustion chamber. You can switch off a pump through which it was coming from the propellant tank. So the burning will stop. The engine gets switched off. You can switch it on again by again starting your pumps and pushing fuel and oxidizer into the combustion chamber and start the burning again. So this is what is liquid engine. And third over here, what you see is cryogenic rocket engines. So the difference between a liquid engine and a cryogenic rocket engine is that cryogenic rocket engines have the fuel and oxidizer at extremely low temperatures. And when I say extremely low temperatures, I mean minus 170 degrees Celsius to minus 220, minus 230 degrees Celsius. At these temperatures, we can store much higher quantities of fuel and oxidizer, first of all, in the propellant tank, because they become much more dense. They are highly pressurized. Second of all, the temperature difference between unburned fuel and oxidizer to the burnt reaction creates a whole another set of energy output. The whole reaction becomes much more efficient. Your mileage increases drastically. Your specific impulse increases drastically. And you can draw much more kinetic energy out of the system than compared to liquid engines. So this is like a cryogenic engine is like a much more efficient, much more advanced, a much better liquid engine. But at the same time, at the end of the day, cryogenic engines are liquid engines. The fuel and the oxidizer are stored in liquid sort of state of matter. And this is, even though this is classified as a different engine, one might have a question that, sir, cryogenic engine is also a liquid engine, and the answer will be yes. but it's a much more efficient, much better, and much sort of a much more useful rocket engine compared to just a liquid engine. So this is basically me trying to explain that how first we have chemical energy, we burn these chemicals to convert it into heat energy. This is a high volume of gases. We then pressurize these gases, convert it into a low volume, pass it through the nozzle. These hot gases escape through the nozzle and provide momentum to the body of the rocket through Newton's third law of motion. This is, you see this same principle being applied on a jet engine first. So in jet engine, you have in the front of the jet engine, you have air at pressure P naught entering at velocity V naught, and then you mix fuel with it. And so in a jet engine, you have fuel like kerosene, and the air provides you with oxygen. So you burn the fuel mixed with air, and then you push out the burnt mixture from a nozzle at VE, ME, PE, and AE. So and then you equate the momentum. This extra momentum or the extra force that you're getting is what provides you with the force that pushes the jet engine forward. But over here, you will see a negative term that is coming because of the air intake. Because we are taking in air at P naught and V naught, like initial pressure and initial velocity. So there is a negative term that is coming in. In case of a rocket engine, we do not have this air intake, and because of this V naught and P naught term is not there, and the only equation that is left is that the force that you will get is based on the ejection of air at PE and VE from an area AE. So that is how that equation changes when it starts getting applied to rockets. So that is what you see over here. And this is specifically for a solid rocket engine. So you have the mass of ejected particles being pushed out at velocity VE. You have P naught as the pressure of the air around you. You have PE as the pressure of the gases which are exiting your rocket. And that difference in pressure into AE is another additional component of the force that's pushing your rocket forward. So even though it might seem a little counterintuitive, if you were to derive this equation to find out what is the maximum force that you can get, you will get that for maxima value, your PE equal to P naught. So this second term becomes 0, and you have VE as a very, very high value in that, and you even have M dot E as a very high value in that, and that is where you get the maximum force from a rocket engine. So that is why you will see that a lot of people talk about sea level optimized rocket engines and vacuum optimized rocket engines, because PE equal to P naught. P naught is atmospheric pressure. At sea level, that is 1 atmosphere. In space, that is approximately 0. So the pressure of exit of your gases need to be different. And at sea level or near the Earth, you need that pressure to be approximately equal to 1 atmosphere, whereas in space, you need it to be approximately equal to 0. So to make it approximately equal to 0, you need to expand your flow much, much more. So you need to have a much bigger nozzle. So vacuum optimized rocket engines have a much bigger nozzle compared to sea level optimized rocket engines. And that is why rocket engines that operate in space will have a much bigger area of exit than rockets that operate near Earth. So this is one sort of aspect that starts coming in when you start designing your rocket for higher stages and for space travel. So this is the same thing being applied to liquid engines, where, as I told you, you have, so in a solid engine over here, you can see you have one tank and the propellant is burning. The flame front is burning inside that tank only. The green part is a propellant mixture which has both fuel and oxidizer. Whereas in case of a liquid engine, you have two different tanks, and the first tank is a smaller tank which is of the fuel, and then the blue colored tank which is of oxidizer. You have pumps. You push
both the fuel and the oxidizer into the combustion chamber, have an ignition, pass it through a nozzle, accelerate the flow, and create the force. The equation may remain the same, the functionality changes and becomes a little different. You will see the same thing happening in cryogenic engines as well. The same configuration. You have fuel tank, oxidizer tank, you will have pumps, you will have a combustion chamber, and you will have a nozzle. So now coming to a model rocket engine, which I showed you how model rocketry works. So model rocket engines are mostly a solid fuel engine. This is how they are operating. You have one delay charge and an ejection charge as an extra thing in that. These both are present to deploy the parachute so that your rocket can land back and you can fix a new engine into the rocket and fly it again. So this is the derivation of how specific impulse works. I have already given out this presentation to the organizers, and if any student is interested in understanding the mathematics of it, you guys can look at it. You guys are all IIT students, and so I'm sure this is not something that you want me to get into right now. The students who are interested can look at it. I'm just going to cover the broad aspects of what are the kind of things that go into rocketry, what are the overall design concepts that we apply, and how these engines work, what are the broad equations that we look at. So that's what I've covered up till now. And now this is a basic structure of a real rocket, of a launch vehicle. On the top, you have the payload, which is your satellite, which you want to put into space. Just below it, you have your navigation or your guidance system. This is the system that tells you whether your rocket is going on the correct place or not, correct path or not. Below that, you have the complete propulsion system. So this may be staged into 2, 3, 4 stages. I have shown this as a singular stage over here, but you have your fuel tank, your oxidizer tank, and your engine at the bottom. This is the complete propulsion system. So the mass, this is the way that you define the efficiency of your rocket, where the mass of the payload upon the total mass of the rocket is your mass ratio. So if you look at most modern rockets, your mass ratio, which is how much useful mass. So if your total rocket is 100 tons, you can put a payload of 1 ton. So that's 1%. So your mass ratio will be 1% or 0.01. So in modern rockets, you mostly see this ratio anywhere between 0.2 to 0.3, 0.02 to 0.03, which is 3%, 2% mass. The total mass of your rocket actually gets deployed into the into space. And whereas with modern rocketry, you can make this much more efficient because these are smaller rockets and they have to handle much smaller forces. So you can have model rockets with a payload ratio of almost 20% or 30%, which is 0.2 or 0.3, which can be really fun, and you can do some interesting experiments. But as you make these rockets bigger, more efficient, and try to take them to a higher altitude, your payload ratio can reduce. And this can be simply looked at it from this same standpoint, that if you have the same propulsion system in a model rocket, you can, with a zero payload, you can go to a height of 600 feet. But with a heavier payload, you may be able to reach only 300 feet. So because you've put extra mass, your total height has reduced. But when it comes to rockets going to space, you have to reach that altitude, fixed altitude. You have to reach a fixed speed. And because of that, your total mass that you can put as payload gets fairly limited. So these are the sort of ratios that you look at while designing your overall rocket. The final equation that you saw over there, delta V into VE ln MO by MF, this is called the rocket equation or the Savolsky equation. I showed you the derivation for this in the previous slide itself. And you can look at that derivation in detail and how that applies to your mass ratios and overall how it applies to your propulsion system, so that you can get an understanding of how these systems are designed. So I think I've broadly shown you what the role of aerodynamics is, what the role of propulsion is, what kind of fields that go into it, what kind of rockets we are designing, what model rocketry is and how it can help you, and what kind of things are happening world over with rockets. And I think with that, I will sort of close this up as a talk. Students who want to go into more detail, this presentation gives all kinds of detail on applying physics to this, applying aerodynamics to this, applying each and every force. So you can see all of that. If any students are interested, you can take hold of the presentation and go into all kinds of detail. If you have confusions or if you have any doubts, you can feel free to reach out to me, and we'll see how we can help you. You can apply all of these things to model rockets, and so I would encourage you guys to build out model rockets yourself and start doing these experiments yourself. That's the best way to learn. So with that, I'll say thank you, and we'll take some questions if there are any questions.
So, sir, we have questions received from the Google form. So, Mahir Raval wants to know that why isn't India focusing more on reusable rocket vehicles?
So, reusable launch vehicles is something which is a very new advent technology. It's even though right now we see SpaceX doing crazy and amazing things with it. The first successful landing that they have is less than 5 years ago. It's 2015. So it takes some time for rocket technology to get developed, and I think India already is on a path where there are small groups and small teams in ISRO looking at the viability of these technologies and how we can build systems that can sort of be reused. And it might take some time, but I think we are trying to do it in a very cost efficient manner, and the way that it will work for India. Every country has a different set of problems that they need to tackle. Right now, for the Indian space program, the problem that is there is not the reusability aspect of it. But right now, the problem that we have is trying to create enough capacity to completely supply the Indian market. Just to give you a perspective on this, the problem is not the rockets, the problem is the satellites. We need approximately 65 communication satellites to fulfill the requirements that we already have as a country. We are asking that, okay, the people are asking that, okay, put more satellites so that I can take this data or I can take this communication resource and give more TV to the people, give more satellite phones to the people, give more connectivity to the people, give more internet to the people. But we don't have enough satellites, and the speed of building these satellites is fairly slow because each one of these satellites costs approximately 200 million to 300 million. These are expensive transponders, and a lot of time and effort goes into building this. So right now, I think that is a core problem that our program is working on. But at the same time, there are some small teams and some small subgroups which are already looking at reusable launch vehicle technology, and I'm sure there will come a point of time when we will see a reusable Indian launch vehicle.
Okay, thank you, sir. So the next question is from Ayush Agarwal. He wants to know that why aren't parachute frequently used for re-entry?
So, first of all, if there is a vehicle that is supposed to be reused up until before propulsive landing, so you saw how the Falcon 9 lands back using propulsion, so rocket propulsion. So up until before propulsive landing, we were using parachutes, but the parachute regime has a fixed speed regime. So if you're using parachutes at 4 Mach or 5 Mach, they will not come in handy. They will not help you increase drag. You need to increase drag by creating a lot of heat energy and then releasing that heat energy into the air and converting all your kinetic energy and releasing that away from your main body. And that is how most of our re-entry systems work. So they will have these heat shields which when we are coming back into the air, they create a lot of friction and they burn up and release all that heat into the air and convert all their kinetic energy into heat energy. And only when they come into a regime where parachutes can be helpful or drogue chutes can be helpful, which is approximately somewhere between 1 to 2 Mach, that they deploy these parachutes and create drag. And that happens for almost all vehicles. So you can look at the space shuttle, you can look at the Soyuz human capsule, you can look at Dragon, you can look at Starliner. Almost all of them have parachutes on them, and they use them for re-entry.
Okay, so the next question is from Mihir Raval again. What are the updates on nuclear engines?
So, nuclear engines, first of all, are a very, very different way of looking at rocket engines. Nuclear engines cannot give you very high thrust, but what they can give you is little bit of thrust for a very, 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 very long time. So, you saw how many varies were there. So, like, just to give you a comparison, 1 kilogram of solid fuel will not last you even 1 second. Actually, we are burning, when we are actually using rocket boost, solid rocket boosters, we are burning almost tons of propellant per second. So forget a kg. Even this similar sort of a mass ratio applies even to liquid engines, where we will be burning hundreds of kilograms of fuel per second. But with nuclear engines, a 1 kg nuclear fuel will last you years of burn. But a solid rocket booster may be able to give you, with tons of fuel being burned per second, it will give you tons of thrust. Same thing applies to liquid engines or cryogenic engines. But nuclear engines will not give you tons of thrust. They will give you a much smaller amount of thrust at a much more efficient rate. So that is why nuclear engines are what is called in-space propulsion. So they are engines that will not take you from Earth to space. But once you are in space, then they can be used to take you from one orbit to another, one planet to another, put you on different trajectories and so on. And I think we have seen some interesting proof of concepts in high technology missions by NASA and some by ESA. Actually, I think there was one nuclear engine even on a Japanese mission. But we have not seen large-scale deployment. The technology has not yet really reached a stage where it can be taken up as a system which is reusable, which is usable and highly deployable. Also, at the same time, the system in itself is very, very toxic, and we don't want to put it in Earth orbit, because if you're putting it in Earth orbit and there is some problem, the fallout from the nuclear fuel can be very, very high, because it will fall back to Earth and it can create really toxic and highly radioactive environments. So even if we do start using nuclear fuel, it will probably be used for beyond Earth applications. And the technology right now is not at a stage where it can be taken up by a lot of missions. There are various space agencies and scientists and teams across the world which are working to advance the technology to that level. And I'm sure once it comes to that level, there will be a lot more people using it. If you look at the Mars landing programs, whether it is the Curiosity or the Perseverance rover or the Chinese rover that just landed a couple of days ago, almost all of them used nuclear propulsion, nuclear retropropulsion to slow down the landing systems.
Okay, thank you. So one more question. The Vikas engine is said to be a hypergolic engine. So what does that mean?
So first of all, I am not sure whether the Vikas engine itself is hypergolic, but yes, the PSLV uses hypergolic fuels. I can check up. You can check up. That's a Googleable part, whether Vikas engine is hypergolic or not. But hypergolic fuel basically means that you have a fuel and an oxidizer. And when you mix the fuel and oxidizer, there is auto ignition. So auto ignition basically means that as soon as you mix the two, the reaction automatically starts happening. You don't need to give extra heat or extra energy to start the reaction. Whereas in terms of a non-hypergolic fuel, you have to provide an initial spark or an initial heat to ignite or start the reaction. So that is the difference between a hypergolic and a non-hypergolic sort of fuels.
Okay, and so one more question. What will be the average price of launching a model rocket?
So this is a very interesting question. So if you go to the US, the cheapest model rockets start off at $12 to $13 per rocket. And then you can keep going higher and higher. The more you pay, the more advanced and the more capable your rocket will become. When I started, or when I did my first model rockets, I was in second year in college. At that time, there were no components, no kits, no launch systems, no fuel, nothing available in India. My only option was either I build everything from scratch or I buy something from the US and import it. If you look at buying something from the US and importing it, a basic model rocket costs anywhere between. So the thing that you will get in the US for $12, which is approximately 900, 900 to 1,000 rupees. That same thing you will get in India for approximately 17 to 18,000 rupees, including transportation and including all the other sort of stuff that you will need, launch pad, ignition system, etc. If you start building everything from scratch, it really depends what capability that you're looking to build on. But if you're doing it in a safe environment, so safe environment means that if you're making your own fuel, you have your gloves, you have proper pipette burette, you have safety equipment for your ovens, you have safety equipment for drying, you have safety equipment for ignition and launch. So if you're building all of those things, again, your cost will be 25 to 30,000 on a minimum. If you are so that's the problem that I started solving at that time when I was in second year in college. So that's almost 10 years ago. Today, Rocketeers already makes available a complete student DIY kit, which has a launch pad, which has an ignition system, which has one rocket and a pre-made fuel cartridge. This starts at 2,500 rupees. And we hope to bring that down further. So if you're just asking me that, okay, sir, I want to build one model rocket and what is the minimum thing that I can do and minimum cost that I can do, then I will say 2,500 rupees. You can just go to the Rocketeers website, buy everything and fly a rocket. But at the same time, if you're asking me, no, sir, I want to build something on my own and try and experiment and do something like that. So then I will say that, okay, you may need to spend some 5,000-6,000 rupees where you can start doing some things on your own. But I will at the same time recommend that there are some components like launch system, ignition system that you should buy, and that because building something safe of your own is much more costly, will take much more time, and then there are safety issues. But if you just buy a safe launchpad and ignition system, that introduces a lot of safety into your system, and you can concentrate on building the rest of the rocket from scratch. Your cost would still be higher than buying everything from Rocketeers, but yeah, you could get an experience out of it. So that's what overall it looks like.
Okay, so one last question. What all do we have to consider, or what all do we have to know before starting model rocketry?
So model rocketry is a very, very DIY activity, and two of the most primary considerations are obviously your budget and safety. So if you are sure that you are going to make sure that whatever you do it in a safe manner, you don't hurt yourself, you don't hurt others around you, and you don't cause property damage. And the second factor is obviously your budget and how much money do you have to spend. So because if a lot of students come to me, sir, I want to build a rocket like BPS space, like Falcon 9, it should land back. That's a beautiful idea. You can do that, and it's all you need is a Raspberry Pi, Arduino, some sensors, and some parts, and you can start doing the experiment. But when you really come down to it, your cost will be above 1.5 lakhs just to build out a prototype completely, which is working. So the idea part of it, of doing this, is very nice, but you really have to work out the cost constraints. So apart from that, the second thing is safety. In terms of the physics and the technical side of it, that is something that you learn by doing. You don't learn first and then do. The whole purpose of doing is learning. So the physics of it, the coding of it, the electronics of it, and how that system is working, you learn when you're doing it. So that's not something that you have to learn first.
Okay, thank you, sir. So, Mr. Divyanshu Podar, thank you for explaining us the basics of rocket science, their history, and their technicalities. We were amazed knowing about the complex rocketry and satellite deploy from PSLV, the Falcon 9 boosters landing back on the Earth, and complicated rocket equations, and etc. So, somewhere in the back of our mind, we did feel that This will be an amazing project to work on, but this seemed difficult considering that there are numerous people behind such missions and a lot of funding and a lot of hopes attached to them. But in order to motivate and give a head start to students and young population towards space travel, model rocketry is made accessible via companies such as Rocketeers. After knowing about your company and seeing this webinar, we really want to start a model rocket club as a part of Nakshatra. So once we all will be back at the campus, we are really looking forward to set up and launch model rockets frequently. So thank you, sir, for this session today. It was very inspiring. And many are asking that if they want to contact you anytime further, how can they do that?
So the easiest way is just go to our website. It has a contact us page. The website is rocketeers.in. ROCKETEERS.IN. The website has a contact us page. That email will come to me directly and go to other members of my team as well. So whoever is the most suitable person will respond to you. And you will definitely get a response. Otherwise, if you want to contact me only directly, you can note down my email ID, which is divyanshu@rocketeers.in, 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 and you can reach out to me. And if Nakshatra is starting a model rocketry club, we would be super excited to help you guys. Or for that matter, if anybody else wants to pursue model rocketry, we'd be super excited to help you guys and see how we can sort of figure out a way for you to build something that is suitable for you, that works in your budget, and that gives you some learning and some excitement. Another thing that in the end that I would like to tell you guys is, one thing is, do follow us, subscribe to our social media channels. We are there on Instagram, Facebook, and YouTube. And the second thing is that we are now partners with what is called Blue Origin. Blue Origin is a space company like SpaceX. SpaceX is by Elon Musk. Blue Origin is by Jeff Bezos of Amazon. They have this program called Club of the Future, where they take postcards from students and send them to space on their rocket, which is called the New Shepard launch vehicle. And then they bring it back in a capsule, and then they give those postcards back to the students. So the student gets a postcard from space, a postcard which has been to space, and we'll stamp it that it's been to space. There'll be a Blue Origin stamp and so on. So Rocketeers is a India partner for this program. So if you guys would like a postcard from space, just make a postcard and send it to us. The address is given on our website. And if you send us a postcard, we will send it to space with Blue Origin and send it back to you. You have to put the address on the postcard as your own address, and you have to send it to us in a separate envelope. Anybody who has questions about this program as well can sort of reach out to us as well. If you guys know about Garib Scientist, he's also done a video on it. So you can check that out as well. So I hope that, I'm assuming that there are a lot of people over here who are excited about space and rockets and stuff. So it would be something exciting for you guys to have a postcard from space. It's a prized souvenir that not many people will have. And this is free of cost, by the way.
Okay, thank you, sir. So we conclude our session over here.
Yeah. Great, yeah, nice talking to you guys. I hope you enjoyed the talk. Looking forward to any feedback that might come my way. Thank you.